Okay, here we are, Lab 10. Notice there are 4 wires coming out of the page. We're looking down the ends of the wires. We can move them all around. And you just need to know that wires, so let's take 3 of them out of the way. If we just take 2 of them at a time together, those are attracting each other, and so what you need to remember is wires that attract each other have the same current, so I can put that one up there. This one is repelling, so that's in the opposite direction. And so that one's attracting, that goes up there. And so you can see that there are 2 that repel, meaning opposite direction, and 2 that attract. So these are the 3 that have current in the same direction. That's all pretty easy. If we want to get the force between them, what I ask you to do is move this down here to a certain position. And I won't take, it's supposed to be 5, -4. And I'll just get it there roughly. And then get the other wires out of the way so they're not influencing the thing too much. I won't take too much time to do this. And then bring one down at a time and put this one at 4, so they're 1 centimeter apart. And then you can read in the yellow the force between them. And notice the force is in newtons per meter, so that means the force per unit length. And so what you need to do is find the equation that will allow you to calculate what the current is, knowing the force per unit length. So see if you can find that equation and do the calculation. Okay, in the lab question, you'll see 4 equations. And since we're dealing with the force on a wire, we want this equation. The force on the wire will be the current in the wire, the length of the wire, times the field times the sine of the angle between them. But the field is produced by the other wire, and this is the equation for the field due to a straight current carrying wire. So this expression gets substituted in for B. The sine of theta, since it's 90 degrees, is 1. And since we want the force per unit length, we end up with this equation. But wait a minute, that's not it. Here it is. So the force, I got the wrong one. So mu naught I, this is the I over 2 pi a. Mu naught I over 2 pi a is the field. There's the current in the wire, and the length of the wire. Of course, we're going to divide by the length. And since the currents are the same, this becomes I squared. So we write this as I squared. We bring the L over here. And then we end up with the expression we need to calculate the current in the wire. So exercise 2, we have 2 wires coming that are red with the fields shown coming out of the page, right-hand rule number 2, and we have a 3rd wire, a black wire, which we can move around. And the yellow numbers give us the position of the wire. So I can put it anywhere I want. And I have a slider here where I can turn on the current. So let's put the current up, all the way up in the positive sense to 5 amps. And then as I move the wire around, you can see it now has a field, which is in what direction? Also coming out of the page, right? So, and you can see, if you look at the arrows, you can kind of see where the field is 0. So we want to get the field at the origin equal to 0. And so you move this around until you get the field as close to 0 as you can, and then you read the position of the wire. But you want to do this carefully. You might want to do it 2 or 3 times and take the best average. Then you can change the current. If we put it negative, or values in between, as I tell you. Now I can move the wire around, and so I'm not going to tell you, but you need to find out where this has to go such that the field at the origin equals 0. Okay, I shut the field off. So now we're just seeing the field due to the two wires, and notice that at the origin it's in this direction. So how do we understand that, and how do we calculate the strength of it? So if we look at the wire on the left, let me go to this. You see the current circulating this way. So at the origin, this wire should be in that direction, right? This is an important skill that you got to get. This is, whoops, yep, that's right. Circulating this way, so wire on the left has a field like that, tangent to the radius. It's a circle, right? And this wire has a field like that. So you can see that there's two vectors, one this way and one this way. The y component here is going to cancel the y component there, and the two x components are going to add, giving you a field this way, and that's what you need to calculate. So what we need is, we need the black wire to have a field which is going to be in the opposite direction, right? Going this way to cancel that field and get it to 0. So for the current to be going this way in the wire, that's counterclockwise. The wire has to have current coming out of the page, so we set it at a positive value and we find the location, and so we can solve this problem mathematically as well. So now we move on to problem 3. This is a real Ampere's law problem. Notice we have Ampere's law, and so this is what we're trying to learn in this exercise. This is a line integral. A line integral means two vectors, like work is a line integral. It's a force times the distance. This is the magnetic field times the displacement vector, and we do it around a closed loop. So we're going to integrate a path around a closed loop. Every little step along the way we're doing this b dot ds. That means b, the field as a vector, times the little ds vector times the cosine of the angle between them. And what Ampere's law says, no matter what path you do around a closed loop, as long as the current inside that loop is the same, you're going to get the same path integral. So let's see what that looks like. 4 wires, green, magenta, cyan, that's the light blue, and yellow, all showing the field so we can get the direction of the current. And we have a little cursor which I can move around and put at different positions. So let's do a loop around the green wire first. So let's put the cursor at some position like, I don't want to spend all day on this, but say 0, 2. Now I'll turn the integral on, because this is going to numerically integrate the path that I follow. Whoops, not getting it. There it is. Let's see if it works. Let me pause the video. Okay, try again. Turn the integral on. There's my pencil. Grab the pencil. Trace a closed loop. It's kind of a circle. Back. And there's the value of the integral. I didn't exactly close it. When you do this, you'll be more careful. But you can see that I got a value of an integral of 612. It would be a little higher if I closed the circle. So you want to do this carefully. Now one of the things, and I encourage you to play around with it. So let's turn the integral off. Whoops, wrong thing. Turn the integral off. Take our little cursor, you see the circle isn't closed, and bring it down here. Turn the integral on and try a different path. Much bigger one. Close the circle. Pretty close. And you see I got an integral of about the same value. It's a little bit higher, probably. And so you're going to do this for each one. And you should draw circles of different sizes. You can draw squares, you can draw rectangles, triangles. As long as you do a closed path around that green wire, the value of the integral you get will be the same according to Ampere's law. The reason is because you're enclosing the same amount of charge. And knowing the value of that integral and knowing the constant mu naught, you can calculate the current in the wire. Problem 4 is pretty easy. It just asks you to calculate this path integral for a square. This is a chance for you to make sure you understand that path integral idea. So there's 4 sides, and if we start in this corner and we follow the path around this way, this side, you see the field is constant, and it's in the direction of the displacement. That's our ds, ds, ds. The field is the same, and so we don't need to do an integral. We just need to multiply the field times all the ds's, which is the total length. When we get down here, we see that the displacement is down and the field is right and the angle's 90 degrees. So the cosine of 90, right, the dot product of perpendicular vectors is 0. Here we're going to get a negative number, and here we're going to get 0. So you can see that the closed path around here should sum to 0, and that's no surprise because there's no current inside. The field is just straight across the loop like that. Okay, last item. So this gray area is a wire with current uniformly distributed through the wire. And you can see it's going into the page using right-hand rule number 2. And then we have a loop. We can integrate around this loop, and like we did in the last problem, and find the field, only that's done for us. So as we change the size of the loop, the graph over here will graph the field value at the location of the loop. So it's important to realize that because the field is circular around the center, that the value of the field everywhere on the loop is going to be the same. Of course, if we change the size of the loop, the field will be weaker. So the integral here, it's a smaller loop but a stronger field. Out here, it's a bigger loop, so the integral of ds is greater, but the field is weaker, and we get the same value because the same current inside. But when we go inside the loop, then the current inside the loop becomes less and less, the loop, smaller and smaller the loop gets, so the field is going to get weaker and weaker. And that's what we're going to see. So let's watch the simulation, see if I can get this to work. Whoops. Go back to this, turn this on, and see if I can do this. Yeah, as I slide the loop this way, it plots the field out to where the loop is as large as possible. And as I bring the loop down to 0 at the center, the field goes to 0. So the purpose of this exercise is to understand and explain this behavior.